So good evening everyone, and this is lecture number 5 in work, power and energy, and we are dealing with the last class we had seen what we had done in the last class. Can you remind me what we were doing in the last class?
Potential energy, sir.
Great. We were dealing with conservative forces and potential energy, and we had seen some relation between potential energy, force, and we had seen how to find out potential energy from force and from force, how to find out the potential energy. Yes or no?
Yes, sir.
Now we come to this sort of last part of this chapter, which is law of conservation of energy. Now, what do you mean by law of conservation of energy?
Energy
Law
can
of, yes, say.
energy can neither be created nor be destroyed, but can transform from one form to another.
Yes, that is the law of conservation of energy. So everyone knows this law of conservation of energy. We have heard this since we were very young. Law of conservation of energy. It states that energy cannot be created. Energy can't be created. We cannot create any new energy nor destroy it. It is only transformed from one form to other. Right? This basically tells us whatever we do, we cannot create energy. Whatever energy was created during the Big Bang, same energy remains in the universe. It just converts from one form to the other form. Now, this is used everywhere. We always use this law of conservation of energy whenever we have to find out something. How much energy is getting converted into this form, or how much energy is getting converted into that form. We use this law of conservation of mechanical energy. In this chapter, though, we will be using another sort of conservation, which is not known as law of conservation of energy. That law is known as what? What are we going to study in this chapter? So first of all, what we need to understand is a concept of mechanical energy. Whenever this comes, mechanical energy is related to mechanics. So this mechanical word relates to mechanics. What do you mean by mechanical energy? You would have heard about this term, mechanical energy. What do you mean by mechanical energy?
Summation of potential energy and kinetic energy.
That is correct. The sum of potential energy we define by U plus kinetic energy, you can define it by K or Ke. The sum of potential energy plus kinetic energy is known as your mechanical energy. Now, this potential energy, as we know, and we are going to see in the course of this entire course, that this potential energy that we are going to deal with is basically going to be of three types. What are the three types of potential energy that we are going to deal with? We've already seen that. We've already seen the three types of potential energy that will be dealing. What are the three types of potential energy that we are going to deal? One is known as gravitational potential energy. The other one is known as spring potential energy. And the third one is known as electrostatic potential energy. These are the three types of potential energy that we'll be dealing through the entire course. Out of this, right now we are concentrating on the two, gravitational potential energy and spring potential energy. The electrostatic potential energy will come in the chapter of electrostatics. Then we will think about that. This is what we call as mechanical energy. Now then, Once we have understood mechanical energy, then we have something known as law of conservation of mechanical energy. Law of conservation of mechanical energy. In short, I will call it LOCME, law of conservation of mechanical energy. LOCME. Now, what does this LOCME say? Yes. What does the law of conservation of mechanical energy say? Mechanical energy cannot be created, mechanical energy cannot be destroyed. It can be transformed from one form to other. Yes or no?
Yes, sir.
No, that is not the law of conservation of mechanical energy. Then what is the law of conservation of mechanical energy?
Total mechanical energy of the system remains same.
Total mechanical energy of the system
Remains same.
always.
Yes, sir.
There is this thing which is at a height. What type of energy it has?
MGH, sir.
Gravitational potential. Now it falls. Where is the energy gone? What energy it has now? Compared to this point, it has zero energy. Where is the energy gone? Is it conserved?
Sir, in the form of velocity.
ठीक है. Up till here it was velocity, but after this, if your law of conservation of mechanical energy always holds true, it should have some sort of energy here. Where is that energy gone? That means half knowledge is very dangerous. Law of conservation of mechanical energy states that, and the most important point is this: in the absence of what? In the absence of non-conservative forces, and we know what are non-conservative forces: air resistance, friction, viscous force. All these are non-conservative forces. In the absence of non-conservative forces, or if they are present, then the work done by non-conservative forces, if it is zero, in some cases the non-conservative forces may be present, but the work done by those non-conservative forces may be zero. If in the absence of non-conservative forces, or if work done by the non-conservative forces zero and only conservative forces are present, and if only conservative forces are present, and if only conservative forces are acting on a body, then the mechanical energy of the body or the system remains constant. This statement is known as the law of conservation of mechanical energy. So it is subjected to a very important condition. And what is that condition it is subjected to? Absence of non-conservative forces, or the work done by non-conservative forces is zero. So if this happens, then you can say potential energy at any point A plus kinetic energy at any point A will be equal to potential energy at any point B plus kinetic energy at any point B. That will be equal to total mechanical energy at any point. This law or this statement is known as law of conservation of mechanical energy, but this is always subjected to a condition that work done by non-conservative forces must be zero. This is only valid when the work done by non-conservative forces is zero, or in other words, non-conservative forces should not be present. Do we understand this?
Yes, sir.
So what are the important points you must remember? The first point you must remember that only conservative forces should be acting. Number two, non-conservative forces should be absent, or if they are present, work done by the non-conservative forces should be equal to zero. This is known as law of conservation of mechanical energy. Do we understand this?
Yes, sir.
Now I call this law of conservation of mechanical energy Locke may. I remember it this way. I call it the Daughter theorem. I call this theorem or this law as the Daughter theorem. It is a daughter, and this daughter is only work. This daughter is only useful when the work done by non-conservative forces is zero. If there are non-conservative forces present, and if they are doing any work, then this Locke may cannot be applied. Then how can you solve a question where friction is present? The only way, one of the ways in which you can solve the question is by what? Work energy theorem. It is always valid, and I call it the mother theorem. So from this mother theorem, we have arrived at this daughter theorem. It's always valid. So you can apply work energy theorem whether conservative forces are present, absent, non-conservative forces are present, absent. You can always apply work energy theorem in that question. But if only conservative forces are present or non-conservative forces ka work done is zero, then you can solve the same question with the concept of law of conservation of mechanical energy. Do we understand this?
Yes, sir.
Okay, I'll give you 2 minutes to note this down.
Done, sir.
Okay, then. What are we going to do is to see how we can use this. So let me go back to the same question that we did sometimes before. We have a block of mass m kept at rest at a height h above ground. Now I release this block. Can't see it, I think. So I have a block of mass m at a height h. It is kept at rest. Now this block is released. So what is going to happen is that this block is going to fall down. When it falls down, before touching the ground, after touching the ground, what happens is a different story. Before touching the ground, it will have some velocity. What is the velocity of this stone before touching the ground? I think we have done this question, but we'll try it again and we'll see how we can use two things together. So I'll give you 2 minutes to give me the answer. Yes, we got the answer.
It is root over 2gh.
Okay, so we can do this question in a variety of ways. The first way is I can apply work energy theorem from point A to point B. Work done by all forces is equal to change in kinetic energy. What are the forces acting here? There's only one force acting here, which is gravity. Gravity is trying to pull it down. The work done is plus mgh, yes or no?
Yes, sir.
Is equal to change in kinetic energy. Final kinetic energy is half mv square. Initial kinetic energy is 0. So from there you will get velocity, which with it falls is root over 2gh, yes or no?
Yes, sir.
But now here, since we see that there is only one force present, and that force is gravity,
Gravitational force.
we can now, which is a conservative force, we can now do the same problem in a different way, not different way, the same way, by using the law of conservation of mechanical energy. So now I apply law Lockme from the point A to B. Lockme from the point A to B. Lockme says that potential energy at point A plus kinetic energy at point A should be equal to potential energy at point B plus kinetic energy at point B. Remember, gravitational potential energy absolute value does not exist, so I have to take some point whose potential energy is 0. So I take this point as gravitational potential energy 0. Then what is the potential energy of point A? It will become plus mgh, yes or no? Kinetic energy at point A is 0. Potential energy at point B is 0. Kinetic energy at point B is half mv square. You do it this way also, you will end up with the same result. Remember, left hand side equation we can always apply. The right hand side equation we can only apply when conservative forces are present. Do we understand this? Yes or no?
Yes, sir.
Okay, then this is a question which has come in previous many engineering exams, including JEE. So I'll give you this question and I hope that you can give me the answer for this one. I cannot change the values of the question because the question has come in a previous exam. So the value might be requiring you to solve it. I can't help it. This is the question and your time starts now. A boy is sitting on a swing at a maximum height of 5 meters above ground. When the swing passes through the mean position is the lowest point of the swing, which is 2 meters above ground. What is the velocity with which it's like a swing? A boy is swinging on a swing. So when it is at the highest point, he is at 5 meters above ground. At the lowest point, he is 2 meters above ground. What is his velocity there? G has to be taken as 9.2, 9.8.
Sir, it is 7.6 meters, sir. Hello, sir.
So how are we supposed to do this? If you want, you can we can draw a simple diagram also and apply lock may. So how does the diagram look? Draw a simple diagram like this, and I hope this diagram justifies everything. So this is the diagram that you can draw. This is the highest point, point A. This is the lowest point, point B. You have to find the velocity at point B. You can look at the forces that are present here. There are two forces that are present here. One is gravity. The other one is tension in the string, but tension in the string does not do any work because it is always perpendicular to the motion. Yes or no?
Yes.
Now you can either apply work energy theorem or you can apply Lockmey. I will apply Lockmey here. So I will apply Lockmey from point A to B. Total energy at point A, mechanical energy at point A will be equal to mechanical energy at point B. Mechanical energy at point A consists of gravitational potential energy. I can take the lowest point as 0. I can take ground also as 0. So potential energy at point A will become 5 mg, yes or no? mgh. H is 5. 5 mg. 5 mg. Kinetic energy is 0. That should be equal to total mechanical energy at point B. At point B, potential energy is mg into 2, 2 mg plus half mv square. We don't need m will get cancelled. So the answer will be 6g, I think, will be equal to v square, or v will be equal to root over 6g. Yes or no?
Yes, sir.
So that is how you are supposed to do this. I hope we understand this. Yes or no?
Sir.
Okay, we move ahead and I will devise a problem and I hope you can do that problem. The question number 3. So now I have a wedge like this. The angle, let us say, is 60 degrees, and I have kept a block of mass m on the top of this. Let us say this height is h. I'll call this point as A, and it is at rest here. I will leave this block. What will happen? It will reach the lowest point B. Yes or no? There is no friction right now.
Yes, sir.
When it reaches the lowest point B, can you tell me what is the velocity of the block? You have 2 minutes to do this. Please let me know once you are done.
Yes, sir.
Anyone got the answer? Okay, so what is the answer? Tell me.
Root 2 GH.
Root 2 GH. That is correct. If we look at what are the forces acting on this body, there are two forces. One is gravity mg and other one is a normal reaction n. The normal reaction n does no work because it is always perpendicular. The only force acting here is gravity mg. So now
Yes,
I can apply Lockmey from point A to B. I'm going to apply Lockmey from point A to B. Total energy at point A. Total energy at point A is how much? mgh. Remember, whenever I am calling this, I am saying that the gravitational potential energy of ground is taken as 0. So the potential energy of point A will be mgh. Remember, it does not depend on anything. It only depends on the height. Yes or no?
Yes, sir.
Plus the kinetic energy at point A is 0. So I just write 0. That will be equal to potential energy at point B is 0. Kinetic energy is half mv square. So the answer is there. Yes or no?
Yes, sir.
Let me call this question as question number A. When it was frictionless, it was smooth. Let me make another question here. And in this question, the green question, the coefficient of friction is mu. I ask you the same question again. What is the velocity with which it reaches ground? Now it is not frictionless. It is not smooth. Can you tell me with what velocity it reaches ground? You have 2 minutes to do this. Yes, beta. Any answers? Shall I do it for you?
Sir, it is
Yes, beta.
root 2 G into H minus mu, sir.
This 60 is not coming anywhere or is coming?
Sir?
This 60, do you use this 60 here anywhere? Is this coming anywhere or not? Or it is useless? It may be useless. I am not saying that it may not be useless. Is it useless or is it useful?
Useful, sir.
Useful. Okay. How did you do it? Tell me.
Sir?
How did you do it?
Work energy, sir.
Okay, you must apply work energy theorem from point A to point B. Why can't you apply law of conservation of mechanical energy?
Sir, here frictional
Is where friction is present, so where mechanical energy conservation cannot be applied. So basically, it says that work done by all forces is equal to change in kinetic energy. What are the forces acting here?
gravitational force and frictional force.
Gravitational force. So there are three forces acting here. There are three forces acting here. One, two, three. What are the three forces? Gravitational force mg, normal reaction
Yes, sir.
n, and the frictional force F. Yes or no?
Yes, sir.
What is the work done by the normal reaction? You got the answer and now you're thinking?
Yes, sir. Zero, sir. Work done.
Zero, because it is always perpendicular to the plane, so
Yes,
work done by normal reaction is zero. What is the work done by friction? Let us first find out the work done by the gravitational force. What will be the work done by the gravitational force?
GH.
So work done by gravitational force is mgh. All of us know it. Work done by gravitational force does not depend on anything. It only depends on where it is and where it has come. On the height, mgh, positive mgh, yes or no? Now, what about the work done by the friction? To find out the work done by the friction, we have to find out the value of the frictional force. Frictional force will be backwards like this, yes or no?
Yes, sir.
How much is the value of frictional force? Mu
2 into
mg
cos theta.
cos of 60 degrees, yes or no?
Yes, sir.
So how much is cos of 60 degrees?
1 by 2, sir.
1 by 2. So it is mu mg by 2. That is the value of the frictional force. What is the work done by frictional force? Remember, this body is moving here like this, and frictional force is backwards. Will the work done by frictional force be positive or negative?
Negative, sir.
So negative. Negative. How much is this? To find out how much is this, we must calculate the value of this distance. Yes or no?
Yes, sir.
How much is the value of this distance? How much is this distance?
Root 3 by 2h by root 3, sir.
It will be equal to 2h by root 3. It is h divided by sine of 30, sine of 60. Yes or no?
Yes, sir.
So the work done by frictional force would be this value of frictional force multiplied by this. Yes or no? With a negative sign. I've already put the negative sign. So 2 and 2 will cancel. You will get mu mg by root 3. Yes or no?
Sir, into h.
Into h. Yes, that will be equal to change in kinetic energy. Final kinetic energy is half mv square. Initial kinetic energy is 0. M will get cancelled. Whatever is left will be the velocity. So v square will be root over 2 times gh can be taken common. So it's v. I've taken root 1 minus 1 by root 3. Do we understand this? Why it is looking complicated? Because of frictional force coming into the picture. Do we understand this?
Yes, sir.
Okay. I'll give you 1 minute to note this down and then we'll move ahead. Let me know once you are done. Everyone understands this? Yes or no?
Yes, sir.
How many of you got this? Please raise your hands. How many of you got this answer? No one? Okay, not a problem. I'll give you more questions. But first, do this one. Have you noted this down? So I can move on to the next one.
Yes, sir.
This one, sir. This is simple. I hope you can do this. A stone is projected vertically upward from the ground, reaches a maximum height h. When it has a height 3h by 4, what is the ratio of kinetic and potential energies? There is no frictional force here. I'll give you 2 minutes to solve this. Yes, but any answer?
No, sir. Wait a minute, please.
Yes, bacha, do we have an answer? Huh?
No, sir.
No answer. Is it such a difficult question? No good, my dear friend, no good.
Sir, wait.
Should not take so much of time. It's a simple question, beta. Chalo, I'll give you more time. I want you to do it.
Sir, wait a minute. Wait a minute.
Waiting. There is a famous song on waiting. हम इंतजार करेंगे तेरा कयामत तक. So I will इंतजार करो for your answer till कयामत.
It's 3:1, sir.
Nah.
3:1, sir.
Have you read the question carefully?
Sorry, 1:3, sir.
See, 3:1 and 1:3 is a hell lot of a difference. 3:1 gives you -1. 1:3 gives you +4. So basically 3:1 gives you -5. Yes or no? Okay, so how are you supposed to do this? Huh?
Sir, it hides
Yes, sir.
that its velocity is 0.
Arey, why you have to do? Why? See, we have got something known as this brain, and we use it smartly. If we use it smartly, we will understand a lot of things. A, B, this is the point. It reaches maximum height that is equal to h. So we'll throw it with some velocity and it will reach the maximum height. At the maximum height, it only has potential energy. Yes or no?
Yes, sir.
It does not have kinetic energy. Now energy is conserved. So the total energy at any point will remain constant. Yes or no?
Yes, sir.
And that will be equal to mgh. Yes or no?
Yes, sir.
That's it. We only need to understand this. Total energy will always be equal to mgh. Now, at this point, let us say point C, it will have some kinetic energy and some potential energy. How much high it is? It is 3h by 4. Yes or no?
Yes, sir.
So what will be the potential energy at point A?
G3h by 4.
How long should you take to do this? mg into 3h by 4. How much will be the kinetic energy at point E? A.
1 by 4.
Why 1 by 4? Because total has to remain plus mgh. Yes or no?
Yes, sir.
3 by 4 mgh has gone there. So how much has come here?
1 by 4 mgh.
Should it take so much of time that you were doing? So what is the ratio of kinetic energy and potential energy? 1:3, not 3:1. Huh?
Yes, sir.
Remember, beta, please, please, please be careful in doing questions like this. Okay, let's see how you fare with this one. Ready? Then steady. Then go. If we throw a ball upwards, again the ball thrown upwards. These type of questions are in fashion these days. They can come anytime. Boys may not know much about fashion, but girls do. If we throw a body upwards with a velocity 4 meter per second, at what height its kinetic energy reduces to half of its value? Dun, dun, dun. Let's see who gives this. It's good to see you smiling, but with smile you should also give me an answer. That then the smile becomes more better. 2 minutes you have to show me your talents.
Sir, it's 4 meters.
Sir, it's 4 meter. Are you asking me or are you telling me?
Telling, sir.
4 meter, but you see 4 meter. Yes, 4 meter. The answer that I have is 0.4, but here it is coming as 4. So let's see. Must be correct. Okay. How are you supposed to do this? Yes or no? No, yes. There are many ways you can do this. So I did not write the question number. Question number 5, 6. Solution. So basically, at what height the kinetic energy reduces to half? So half will be kinetic energy and half will be potential energy. Yes or no?
Yes, sir.
You have to do it quickly. And the total energy should remain half mv square. Yes or no?
Yes, sir.
So half of half into m into v square is 4 square. Yes or no, bacha?
Yes, sir.
That should be equal to the potential energy, right? Half is kinetic, so half is potential, right? So that should be equal to m g h. Yes or no?
Yes, sir.
See, you apply your whatever, and you get the answer quickly, right? So 2 and 2, 1, 4 will cancel. 4 divided by g is height. 4 divided by 10 is height. So the height has to be 0.4 meters, not 4 meters. The option were given wrong. Do we understand this? Yes or no?
Yes, sir.
So this is how you do it. We will continue with this discussion. Work by energy. We'll do more questions in the next class. Now I will try to complete it. In the next class, there is one part that will remain. That is circular motion wala part. So I am not going to do it separately. We'll do it with rotation. Once we do that, then we'll come back and see some more cases here. Okay? Because we don't have enough time to do one thing twice, right? So
Yes, sir.
I'm not done circular motion. Normally I do circular motion with work power energy because it has some questions which require circular motion. We have not done this. I'm not doing it right now. We don't have time for doing it twice. So what I'll do is we'll finish center of mass. Then we'll start with rotation. In rotation, we will do that part and then we will go ahead. Okay. So that is how you will do it. So that will also be a revision of work by energy after say 3 to 4 classes. Okay. So I will wind up this class here. In the next class with more probability, we will be finishing your work by energy. I've already sent you the sheet. You got the sheets?
Oh, sir.
Sent the sheets 5 days before. Okay, I will inquire and I'll hope that you get those sheets as soon as possible, and I'll send you the next sheets beforehand. Okay, so we'll meet in the next class. Take care. God bless you all. Bye.
Thank you, sir. Have a nice
Bye.
day.
Bye. Try questions. Okay.